if we're thinking about like what's important for the climate system, we can start with the land. So the land's going to be important. The ocean is going to be important. Glaciers or ice on the land. So glaciers refer to ice sitting on land. So you can have alpine glaciers, glaciers in mountains, or ice sheets like the Greenland or Antarctic ice sheet are considered glaciers as well. So just ice on land. We have sea ice, so ice sitting on top of the water in the ocean. Plants are going to be important. Obviously, the atmosphere we're going to talk a lot about. And we can basically cap our two-dimensional diagram with space on top. So this is our 2D diagram of the Earth system. So let's first talk about the atmosphere. Yeah. So which elements is the atmosphere made of? Well, it's mostly nitrogen, and then we have another fraction that's oxygen, and H2O, water vapor, is another fraction. So that gets us to most of the atmosphere. So most of air is made of these elements: nitrogen, oxygen, and then hydrogen in water. And since we're going to be talking about molecules in this class a decent amount, it's good to kind of review this periodic table. And just remember that everything that you see, everything is made out of one of these elements, right? So do you know what you are made mostly out of? Yeah, mostly water. So mostly oxygen by mass, because H2O, the oxygen is much more massive than hydrogen, but mostly hydrogen by the count of molecules, because there's 2 hydrogens in every water molecule. So you're mostly made of hydrogen and oxygen. And let's just review quickly, what does this 7 mean here? It's the number of protons in the nucleus. So this is nitrogen, has 7 protons in the nucleus. So what would nitrogen be called with 6 protons in the nucleus? Yeah, there's no such thing. What these numbers are, the number of protons in the nucleus is it's what different elements are. Like, that's how we define it. So the word carbon is just a label for an element that has 6 protons in its nucleus. So there's no such thing as nitrogen with 6 protons in its nucleus. We call that carbon. Any element that has 7 protons in its nucleus, we call nitrogen. Any element that has 8 protons in its nucleus, we call oxygen. So those are just names for elements with different protons in the nucleus. I'll talk about in the carbon cycle lecture that for the most part we can consider carbon conserved on Earth, that we're not really creating or destroying it, but that's not completely true. We actually do create some carbon on Earth. So it's related to this concept that, like, if you started with nitrogen with 7 protons in the nucleus and you somehow got rid of one, then you have carbon. And that does happen. That does happen in the atmosphere, that we have nitrogen sitting in the atmosphere and we're constantly being bombarded with cosmic rays that can push out some protons out of the nuclei of nitrogen. And then all of a sudden you have carbon, because if you lose one, then you have 6 protons, and now you have carbon. Just a review there of what elements are and what we mean when we say carbon and nitrogen and oxygen. But so the point here is, what is the atmosphere made of? It's made of mostly these things: nitrogen, oxygen, water, argon is another one. But then we have what we talk about much more in this class, CO2. So CO2 is a tiny fraction of the atmosphere in terms of the total amount made up in the atmosphere. So this is in percent. So 0.041% per cent means 100, right? So per 100, that's parts per 100, or 0.041 parts per 100 is 0.41 parts per 1,000, is 4.1 parts per 10,000, is 41 parts per 100,000, and is 410 parts per million. So that's just the same thing. And then the other ones that we'll talk about are CH4. So that's our other greenhouse gas I mentioned, and that's an even smaller percentage of the atmosphere by volume. So even much smaller than CO2. And you'll notice that this CH4, so this is methane, that also has carbon in it. So when people talk about carbon emissions, usually they're referring to CO2 emissions, but sometimes they're kind of pooling these together, methane and carbon, because they both have carbon in there. You'll notice that these greenhouse gases, these ones that we care about, so methane, CO2, and H2O, have kind of a different structure than what the atmosphere is mostly made of, N2 and O2, where these nitrogen and oxygen are these diatomic molecules. And it turns out that's important. So diatomic means 2, so N2O2. And it turns out that's important for whether or not it's a greenhouse gas. And these more complex molecules have these magnetic dipoles. And so it turns out that it's the structure of the molecules themselves that is important as to whether or not they are a greenhouse gas. So we're going to kind of just leave nitrogen and oxygen aside and not talk about them a whole lot, and focus on these greenhouse gases, even though they're a very small percent of the atmosphere. by volume. So we have an atmosphere, we have these molecules in it, these greenhouse gas molecules. And okay, so where is our energy going to come from at the beginning? Where does almost all energy on Earth come from? The sun. So we have our source of energy is the sun. And there are a couple other sources of energy. Yeah, so geothermal, that's energy that is from isotopic decay within the Earth's core. And so that's not coming from the sun. So what I'm thinking of is just other stars. So at night when you're looking up at the sky and you see light from other stars, that's another source of energy. But both of those are very small compared to the sun. So the sun is the dominant source of energy. And you saw this number in the diagram in the reading, 342 watts per square meter. That's how much energy is hitting the Earth's surface, averaged over day and night and averaged over the entire surface of the planet. So that's like thinking of like 300 watt light bulbs per, so square meters, so per like 9 square feet roughly. And this, whenever you see arrows in my slides, that's almost always a flow of something. So a flow means that you're going to have like a unit of time in the denominator. It's something per year, or it's something per second, or it's a flow. And so it's not obvious that this is a flow because the unit is hidden within the unit of watt. But a watt is a joule, which is a unit of energy per second. So what this is saying is 342 units of energy come in every single second per meter squared of the surface of the planet. So it's a flow of energy constantly coming in from the sun.